come on now. All right, where we left off last time was the vocabulary at the end of 2.1, so today we'll be starting with 2.2. But before we get that, I want to know, are there any questions? Anything we've covered so far? Okay, a little bit of a recap on here's the one announcement I did want to make. This should have been the rule, but it's been this term more of the exception. I should be on the campus, Birmingham campus, this Friday. I haven't been there. Last Friday I had a doctor's appointment. The Friday before that I had professional meetings. It seems like maybe the Friday before that I was on the Birmingham campus, and then the Friday before that I had a treatment. No, I guess I had a treatment and then was on campus and then had 3 treatments in a row. So I've only been in the last month and a half or so on campus once, and this Friday will be the second one. So I should be there this Friday from 7:45 until 11:45 at least. Now, there is some meeting that they said is mandatory for us to go to. I've been trying to relocate the email so I can find out, exactly what time it is. I found the reminder of it, but they didn't have the time on that one. So I've got to keep looking for the email to find. I hope I didn't delete it by mistake. But anyway, I will be in a meeting part of the time on Friday. So that's how it goes. Last Friday, shucks, I missed a meeting because I had a doctor's appointment. But anyway, it's just crazy. Okay, any questions before we get going today? All right, 2.1 vocabulary. Top of page 120. Linear, constant, and squaring functions are examples of blank functions. There's several words you could put in there. Linear, constant, and squaring functions. Functions are examples of, and if you look at the title of the chapter, polynomial functions. The squaring functions are quadratic, the linear and constants are not. But quadratic functions are now. Also, they could be called, maybe not linear, but I was saying the constant function and the squaring function could also be called parent functions, but that was back in chapter 1. We're not using that terminology right now. Number 2, a polynomial function of x with degree n has the form of f of x, that's the function form, is equal to a sub n, where that n is just a counter, a is the coefficient, x raised to the nth power. That n is an exponent. That's part of the problem. Plus a sub n minus 1, a counter, times x to the n minus 1 exponent, plus, and you keep going down on the exponents until you get to a sub 1, x to the first, a sub 0, of course x to the 0 is 1. The only requirement here is a is any real number, except a sub n can't be 0. You have all these a's there. A sub n can't be 0, otherwise it's not going to be a polynomial degree n. Where n is a blank blank. What is the characteristic of n for this to be a polynomial function? Hint, it's the exponents of your x. What does n have to be? I think I recognize her. Okay? Haley's here. All right. Talk about polynomial functions of degree n, where n is the exponent of the variable, say x. What does n have to be? Positive. What else?
Number.
Positive number for sure, but what kind of a number? These are polynomial functions. Say again?
The exponent?
It is an exponent. It is the exponent. Has to be positive. And the other thing it has to be is, here's the question. Can it be a rational number? No. So it would have to be an
Irrational.
Say again?
Irrational number?
No, that would be even worse, okay? A positive What kind of number?
Even.
Not even. It could be odd. Integers. You could have also said whole numbers. That's positive integers, okay? You could have said counting numbers, but they use positive integers. And a sub n minus 1, and all those down to a1 and a0 are what kind of numbers? The coefficients can be what kind of numbers? All real numbers. Now, we don't want any imaginaries in there yet, but all real numbers. Absolutely. Okay. Number 3. A blank function is a second-degree polynomial function. What's that? Quadratic. And its graph is called a parabola. Got it. Number 4. When the graph of a quadratic function opens downward, the leading coefficient is blank. Negative. And when the vertex of the graph is a
Upside down.
the vertex. What is the vertex?
Oh, it's the maximum.
Maximum. It's a maximum. Exactly. All right. Now, I've already assigned those homework exercises to you. Let's move on to section 2.2. 2.2 is polynomial functions of higher degree. The last section, we dealt mostly with quadratic functions, degree 2. Now we're going to go to higher degrees, now that Melva's here. Okay? All right. And Monica, if I can find you. There you are. All right. Anyone else come in since the public? Okay. So we're going to look at higher degree polynomials. Now, what was nice about quadratics, a lot of times you can factor them. And even if you can't factor them, you can use a quadratic formula to determine their zeros. Okay? They made nice, very regular things. You can write them in standard forms. You know, there's just all sorts of nice, convenient things about these low-powered, low-degree polynomials. But when they get higher degree, you start losing some of those advantages. So, what we're going to look at first is using transformations. They love these, don't they? You know, to sketch graphs of polynomial functions. And then we're going to look at something, a leading, and I don't like this term particularly. They call it the leading coefficient test. I like to call it the leading term test, because you're going to use everything about that leading term, not just the coefficient. Coefficient tells you one piece of information, well, maybe two pieces of information. The leading term tells you just about everything you need to know. Not everything, just about. To determine the end behavior of the graphs of the polynomial function. So it's not just the coefficient, you need that whole leading term to tell you that end behavior. We will find and use real zeros of polynomial functions as sketching aids, and because we love to sketch our graphs, don't we? Yes. Okay, I knew you did. All right. And finally, we'll use the intermediate value theorem to help locate real zeros of the polynomial functions. Okay? So we'll start with, guess what? Graphs of polynomial functions, our favorite. In this section, we'll study the basic features of the graphs of polynomial functions. And believe me, these are helpful. Okay? There's the old saying, pictures are worth thousands of words. You often hear it called, a picture is worth 1,000 words. The actual original of that was thousands of words, okay? And truly it is. If you can picture what the graph looks like, you know a lot more about the function just looking at coefficients and exponents, okay? Basic features. The first feature of a polynomial, every polynomial function, is that the function is continuous. What does that mean? Say again?
It doesn't end.
It doesn't end, and it doesn't have any breaks in it. It doesn't have any gaps, you know. Now, that's not the only one. We'll have one other really important feature, but they're going to wait a slide or two to give you that. So essentially, this means that the graph of the polynomial function has no breaks, no holes, no gaps, okay? And this is an illustration of one. as you said, you don't have a dot here at the end. It just keeps on going down this way, so it has no end. It comes up and down. I'm going to go out and tell you the second feature because I think it's just as important as the first. They're also smooth functions. No angles, no points, no cusp. Everything is a smooth continuous function. No places where you have sudden abrupt turns. All the turns are rounded. That's true about polynomial functions. There are other functions that have that same feature, but polynomials, all of them do. So the graph shown here in figure 2.6b is an example of a piecewise defined function that is not continuous. Now this piece may be a polynomial function, that piece may be a polynomial function, but the overall piecewise defined function in this case is not continuous. Okay? Functions with graphs that are not continuous are not polynomial functions, even though the individual pieces might be polynomial functions. They don't have to be, but they could be. But even if they are, the function itself is not a polynomial anymore because it's piecewise. It has a gap, it has a break, it has a hole in it. Okay. Now, the second feature here, I told you they were coming up with, well, I just had to say it earlier. Second feature is that the graph of a polynomial function has only smooth, rounded turns, as shown here. Notice there's no points, no peaks, okay, no cusps. They all, even when it's fairly sharp, it's always rounded, okay? That's important. Rounded, rounded, rounded. All the turns, all the bends, all the changes in directions are gradual in some sense. They are not just going up and then changing abruptly and coming down. It's rounded at the top or bottom. Okay? So smooth and continuous. If you keep those two names in mind, that makes your life with polynomials a lot better. Okay. So here's an example of one that's not. Polynomial function cannot have a sharp turn. This is the good old favorite. Okay. Those vertical bars. Absolute value function. Okay. Nice handy function. It's f of x is equal to x anytime x is positive. But if x is negative, the absolute value of x is negative x, because it's always got to be a positive number. So down here at 0, 0, you have an abrupt turn. That's not a smooth transition. It's coming out straight here, going out straight there. You have a sharp turn, okay? A 90-degree turn, in fact. You know? So graphs of polynomial functions cannot have a sharp turn like that. So absolute value function will not be, I want to say never be a polynomial function, okay? So the parent function of this absolute value of x has a sharp turn at the point 0, 0 is shown. This is not a polynomial function. F of x equal x, that would be a polynomial function, linear. F of x equal minus x, that would be. But that sharp turn at the origin means the whole function is not. The graphs of polynomial functions of degree greater than 2 are more difficult to analyze than those with degree 0. What do we call a polynomial of degree 0? That's a special name. Mentioned it already today. Constant function, okay? Degree 1. Second. Linear function. And degree 2. You said it today. Second. Degree 2 polynomial. They have a formula we use on them. You said it earlier. Yeah, it is a squaring function. It's 1, but more complicated. Ax squared plus bx plus c, that's one of these.
Absolute.
Say again?
Absolute. No, it's not.
Y'all have said the word today already. What was the title of 2.1? That section. Quadratic functions, of course. Okay, that's degree 2. Constant function, degree 0. Linear function, degree 1. Quadratic function, degree 2. Anything higher than that, a little more effort to get determine what the graphs look like. However, using the features presented in this section, coupled with your knowledge already of point plotting, yes, y'all are good at that. Intercepts, yes, very good at that. Symmetry, we'll do a little bit of that. You should be able to make reasonably accurate sketches by hand. Okay, and that's the thing here. The polynomial functions that have the simplest graphs are the monomials of the form f of x is equal to x to the n. For n is any integer, okay, greater than 0. That means positive integers. Remember, we said that today already. Now, these are also called the power functions. Now, if it's degree 2 or less, we've already talked about those. But when the n is 3 or more, then these are the upper levels. So let's start with sort of the parent functions for these power functions, okay, and see how they look, okay? Now, in this figure, when n is even, like a 2 or a 4, they sort of look alike, don't they? Okay, we already know what this is when n is equal to 2. What's that function called? Say again? It's a quadratic function, and its shape is a what? Parabola, exactly. And this is the parent function, the squaring function, just x. Oh, here comes a horde. Okay, great. Okay. All right. Gavin is here. Okay. Yeah, they got Brianna. I was going to see if Denisha. Kelsey. Okay. Okay. All right. Anyone else come in while I wasn't looking? Okay, good deal. All right. We're just talking about higher order polynomial functions. We're comparing the squaring function, which is a quadratic function, y is equal to x squared, this nice, smooth, rounded parabola, with y is equal to x to the 4th. Higher order power, but even. Okay? Look at it. Because x squared is always what kind of a number? When you square any real number, what do you get? Positive. So you see, this never is negative. Okay? Could be 0, but never negative. Okay? Unless you have a minus sign in front of this, and then it flips it all over. And here is Tadarius. We got to find you. There you are. Okay. Anyone else come in and says, okay? So there's your quadratic function. Okay? When you do x to the 4th, it's also always positive. Because if you raise any number, any real number, to an even power, you're always going to have positive result. So this also stays above the x-axis. Unless, of course, you had a minus sign in front, which then would flip it across. Okay? And if you did an x to the 6, it's going to look fairly similar. Now, here's the differences. Okay? 3 points are in common. 0, 0. Yeah, that's going to be true of every one of them. 1, 1, when you square 1, raises the 4th power. Or when you do negative 1, square it, it's 1. Negative 1 to the 4th power is 1. But other than that, none of them are the same. And what happens here, the higher the power, the steeper the curve is outside plus or minus 1. Okay? It goes up much more steeply. The higher the power, the steeper it goes. Okay? The other feature is near 0, the higher the power, the flatter it is. Okay? If you think about it, take it looks sort of like CJ as I remember him looking, or something like that. Okay. There we are. Anyone else come in, Sister Caldwell? Okay. So, that's the feature of even power functions, your power function, x to the n, where n is an even number. Let's go to an odd number. Now they're skipping 1. 1 works okay, but it doesn't quite look the same. If x is equal to 1, you have what they call the identity function. Just that straight line, linear function. Anything higher order has got to have curves to it. So that's why we sort of skip 1. But if you use x cubed, the cubic function, again, you have 3 points in common for all these power functions that are odd. 0, 0 is always going to work. 1, 1 is always going to work, just like it worked here. But now negative 1 will produce a negative 1, because if you raise a negative number to an odd power, it goes minus, plus, minus, plus, minus, so every odd power is going to be negative. So these will be down here. So these have negative results and positive results. Even power functions only positive unless the leading term is negative, and then it flips them over. Okay? So the cubic function looks like this. And, if we put the linear function in there, it would go through negative 1, 1, 0, 0, and 1, 1. It goes through those 3 points too, but it has no curve in it. The cubic function has a little bit of curve. It almost looks like half a parabola coming up here, but at 0 it turns and becomes the other half. They're not parabolas. They look sort of like it, but they're not. Okay? But then when you do x to the 5th, it comes up steeper outside plus or minus 1, just like x to the 4th was here, and flatter near 0. Okay? So that's what your power functions that are odd, n is odd number, that's what they're basically doing. Okay? Here's what they're saying. When n is even, the graph of y is equal to x to the n touches the axis at the x-intercept, which here happens to be 0, 0, but doesn't cross. It touches it and goes back in the same direction. When it's an odd function, when n is odd, then it goes up, touches it, and then crosses it. Okay? So it does cross the y-axis. Now, trying to think, no, we didn't do this in chapter 1. We're going to be doing it later in chapter 2. We didn't talk about multiplicity, did we? No, we'll do that coming up now. Okay. I think we're ready for, oh no. Moreover, the greater the value of n, the flatter the graph is near the origin, and the steeper it is outside plus or minus 1. Okay? So, I'd already said that. They chose to say it. So what are we going to do now? Let's make a graph of each of these functions. Now, what we're doing is taking what we just talked about, but then doing some transformations to them. So, there's a couple ways you can do this. I'll let you choose which way you want to do it. Do you want to first graph the parent function, or you want to just tackle this one as it is? It's up to you. Tackle it the way it is? Okay. So let's do. I'm probably still going to make reference to the other. Okay. Let me just put a few points on here, because we know they're going to be important. The origin is 0, 1, negative 1. I say negative 1 and write negative 2. Something's wrong with this old brain. Okay. All right. And we'll plot a few more points here, though we're not going to really need them. Okay, and we'll go up 1, 2, 3, 4, 5, down 1, 2, 3. Okay. Now, give me a point that's on the graph of f of x. If y'all don't want to do the parent function, we'll just go straight to that. What's a point that's on f of x? A really easy one. 2, you say? When x equals 2, what's f of x? 2 to the 5th power is 32. 32. I can't draw that one on this graph, okay? Not easy enough for me. So let's not do, and it's a minus, because you raise 2 to the 5th power, it's 32, but then you negate it. So, but a minus 32. I can't draw that one on here either. So let's do x a little bit less than that. Second, 1. Okay, and what's alpha of x? Negative 1, okay? So 1, negative 1 is going to be on that curve. Got it, okay? How about another one? Negative 1. And what happens if you... It becomes a positive 1. Perfect. And one more. Y'all skip the easy one. 0. What does 0 become? 0, of course. Okay? Now we know the 2's are going to positive 2 on the left, negative 2 on the right. 32. We're not going to get there. So let's bring this down really sharply here. And then when it gets close to x origin, it flattens out for quite a ways and then goes really sharp down again. Something like that. There's your alpha of x equal minus x to the 5th. If you think back to the earlier figure we had, x to the 5th was going up like that, and this just flips the whole thing across the y-axis. So that's a reflection across the x-axis. Okay. Let's go on and look at what the book does with this one. I'll erase this so I'll do it now so you can remember. Here it is, okay? Because the degree of f of that is odd, it has a graph similar to x cubed, but it's steeper and outside or near plus or minus 1 and flatter near 0, the origin. And it's a reflection across the x-axis, so it goes in opposite directions. So there it is. Pretty much what we had. Flat in here, they just have a much bigger scale. Flat in here, steeper outside. Okay? So, let's go back to the B part. Now, why did I draw my x-axis way down there? Ah, yes, because this is x plus 1 with a positive sign in front, raised to the 4th power. Everything here has to be positive, okay? So I won't need those negative numbers. So let's pick a few points here. Plus 1 and minus 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7, positive 1, 2, 3, 4, 5, 6, 7, 8, something like that. We don't need any negatives. All right, generally, what's going to be the shape of this one? Anybody? It's going to look kind of like a parabola. What would be a little different about it? Yeah, it was steeper and flatter, okay? So steep outside, flatter near 0, not near 0. What's another difference here? What do you notice here? Ah, that plus 1. And what is that plus 1 affecting? The x, you're absolutely right. It's added to the x, not the h, which is your y value. It's added to the x. So what does that mean? No, if it was added to y, we go up or down on the y. Say again? Shift left. Absolutely. Remember, anything dealing with x is backwards. So since it's a plus 1 there, we'll shift left 1 here. So that's going to be our origin now. So that's what it's going to be flattered near. It's not going to be the origin. That's going to be our vertex now. So it's going to be flat there. And then what it's going to be, pick me some other points. Okay, at 1, 0, At negative 1, 0, you're going to be 0. Let's see if that works. If you put a negative 1 in here, what do you get? Negative 1 plus 1 is 0, raised to the 4th power is 0. Yes, that's the vertex. Give me another point. 1, okay, 1 is over here. 1 plus 1 is 2, raised to the 4th power is 16. See, you got me off scale again. He loves to do that to me, okay? So give me another one, maybe not quite as high as 1. 0! What happens if you put an x in for 0? 1, right? 1 raised to the 4th is 1. So 0, 1 is going to be on that graph. Okay, very good. Surprise, surprise. How about another one? Negative 2. What happens if you put a negative 2 in for x? Negative 2 plus 1 is? Negative 1 to the 4th power is? 1. Positive 1. So there we have. So it looks just like the last, except you've shifted it horizontally 1 unit to the left. Exactly what you said. So it's going to be steep here, come down here, flattens out here around the vertex, and then goes up really steep again. I don't even have them steep enough, and probably not flat enough. Okay? That's what it's going to look like. Make sense? Every point is shifted 1 unit to the left. Okay? Horizontal shift. Remember those? So here we go. The graph of h of x equal x plus 1 to the 4th is shown here in this figure. It's a left shift by 1 unit, so everything. This would have been x to the 4th would have been a 0, 0, 1, 1, negative 1, 1. Every one of those is shifted left ones. Okay? Make sense? Flat here, steep outside. Good deal. Any others? Any questions? Okay, so that was example 1. Remember, every example has a checkpoint. Okay? There's 4 says to sketch the graphs. Well worth your effort to do those. Soon as you get out of class or have free time, try to get those done. Okay? So what we're going to move now is to what they call the leading coefficient test. I like to call the leading term test, because the leading term tells you a lot more than just the leading coefficient. I don't know why they say coefficient, but okay. In example 1 that we just did, know that both graphs eventually, the first one was like this. It rose to infinity and fell to infinity. The second one rose to infinity in both things. So both graphs eventually rise or fall without bound as x moves to the left or the right. Okay? That is characteristic of polynomial functions. Okay? Because remember that leading term is a sub n times x to the nth power. And the larger the n is, the more rapidly that's going to go up or down, depending on the sign of your x and your a, basically. So, whether the graph of a polynomial function eventually rises or falls can be determined by the function's degree, whether it's even or odd, and by its leading coefficient. Okay? Now, guess what? The leading coefficient, that's fine. Call it leading coefficient test. The leading coefficient tells you nothing about the degree. The leading term tells you about the degree and the coefficient. So what? So the leading coefficient, whether it's positive or negative, indicated by the leading term test, okay? Because the coefficient tells you nothing about the degree. The leading term tells you both the degree and the sign, okay? So, why they call it leading coefficient test, I don't know. So here's what the leading term test is. As x moves without bound to the left or to the right of the origin, okay, the graph of the polynomial function, f of x equal a sub n, that's the leading coefficient, x to the nth, that whole thing is a leading term. So you see, you don't get the degree unless you include the whole term. And then you have all these smaller degrees. Okay? Now, remember we're saying as x is moving without bound to the left and to the right. Okay, I'm not going to go without bound, but let's just take a fairly simple number, 10. Okay? Now, you choose me an exponent here. 4. Okay? Now, as you're taking 10, let's go to the right first. Okay? 10 to the 4th. What's that number? No, 10 to the 4th. 10, no, 100,000. No, 10,000. 10,000, okay? If you go to the left, -4, x to the -4 is x to the 4th, a -10 to the 4th is going to be 10,000 positive again, right? Okay? Now, if that was a third, that next term there, x to the 3rd is 1,000. 10,000 is going to swamp 1,000 every time. And -10,000, or it's going to still be positive, 1,000 is still going to be swamped by 10,000 on the left-hand side as well. I'm using my different hands. So you see this, with very large x's, this is going to dominate. Who cares what the rest of these are? For very large x's, this is going to dominate. So that's why the leading term tells you the end behavior. What happens in the long run, when it's positive or negative, okay? When x is very large, okay. So let's first look at the case where n is odd. You gave me an even. When n is odd, okay, and here's how they express it. I like to lead with as x is approaching positive infinity, okay, as x is getting bigger and bigger and bigger, and n is odd, a very large number, like 10, raised to an odd power is going to be very large x, very large positive x raised to any power is going to be very, very large, right? Okay, so that's going to be positive. If this x, the n again, okay, we're going to assume that this is a positive here. And if this x is very, very large negative, but n is odd, it becomes very large negative. So whatever happens in here, that's determined by these terms, okay? But the end behavior is determined by the leading term. As x is very large, going very large infinity, f of x is going there even faster, okay? When x is going very large toward negative infinity, f of x is going very large negative, okay? Every time when n is odd. And a is positive. A sub n is positive. Because if you change the sign of this, what you do? Flip it across the x-axis. So then it's going down for large x is positive. If this a is negative and n is odd, then the f of x is going very negative. Because the very large positive x is going to be a very huge positive number, but then you negate it and it flips it over to make it negative. Same thing going this way. A very large negative number, let that go very large, raise it to an odd power, that would be negative, but that leading coefficient being negative flips it back positive again. Okay. And again, now I kind of don't like what they're doing here. They're saying as x has a very large negative infinity, it's not even letting it get to negative infinity. It's showing, it shifted these things a little bit too far. I think they should be not centered at the origin, but, shifted this way, because that's where it's going south. You have to go make the x's negative. Okay. Now, I want to point out to you, here's how we describe it. Okay? And this is how you're going to see it on quizzes and on tests. Okay? So look out for it. Most of the time I'm going to say as x approaches blank, f of x or g of x, or these could be t's, whatever you're going to do, is approaching blank, and as x is approaching blank, f of x or g of x or whatever it is, f of x is approaching blank. Now that looks the same, doesn't it? Okay, when you're dealing with polynomial functions, what number, it's not quite a number, it's going to go in every one of those blanks. Infinity, okay? Guess what, folks? You should have some answers right every time, okay? Because this is going to an infinity. This is in behavior. You're going very large numbers. They're all infinities, okay? And I will give you this, too, okay? You'll have to fill it in. One of these x's is going negative and one is going positive. So one of those you put a sign by and the other you leave without the sign. That's your x, right? Okay? So let's just do this one negative and the other one positive. Guess what? You've got half of the problem right already, just by filling in plus and minus infinity for the x's. All you have to do now is figure out what signs go with the y's. Okay? And where do you look? Say again?
A.
Okay, that's part of it. The leading term. And what do you look at the leading term? Two features. The N and the A. That's what you look for. So if N is, what do you consider by N? Odd or even. That's it exactly. So if N is odd, what do you know about the function? It's going in opposite directions. Okay, it's got to. We just don't know which. So what tells you which direction it's going? A. If A is positive, then an N that's negative is going negative. I mean, an X that's negative is going negative, an X that's positive is going positive. But if A is negative, it flips it. Okay? Both of them. Okay? If that A is negative. So there you have. You know they're going to be infinities. Oh, that one didn't show up, did it? I didn't write it. I thought I had. Okay? And you just have to assign the signs. Okay? Now, so that should be some pretty easy points on every quiz, on every test, right? Now this is for polynomial functions. Later we'll be doing the same thing for rational functions, and the rules change a little bit, okay? But for polynomial functions, every one of those blanks is going to have an infinity in them. The two x's, one's going to be positive, one's going to be negative. All you have to do to answer the question is determine the signs of those two y's, the f of x's. One, you can't say what they're going to be. It could be both positive, it could be both negative, it could be one positive, the other negative, or the other positive and the one negative. If n is odd, one's going to be positive, one negative. If a is negative, the one that goes with the negative x is going to be the positive there. If it's a positive x, a negative. If a is positive, then the signs will be the same. A negative x will be a negative infinity for f of x, and a positive infinity for x will be a positive infinity for f of x. Just like it shows here. Okay? This is for n odd. Okay? Now, guess what happens for n even? These functions, if n is even, you're either on the up and up or down and down. They're going in the same direction. What determines which way they're going? The sign of A. Exactly. So you use the entire leading term first to see what n is, even or odd, and then what A is, positive or negative. Now notice here, if n is even, okay, again, your x's are going to be a negative infinity and a plus infinity every time, okay? If n is even and a is positive, then these f's are both positive. They've got to be. They're all infinities. they've got to be positive because the even function, they're going in the same direction, leading coefficient positive, they got to be on the up and up. Okay? However, if, and again, this is the same thing, your x is either negative infinity or positive infinity. Okay? If it's an odd, even n, they're going in the same direction, so a negative coefficient is going to put them down. Both of them going down. So for x negative infinity or positive infinity, your alpha of x is going to be negative infinity both ways. It's got to be the same because that x is even. You've got to go with the sign of your a. Same thing. Okay? So let's go back and sort of summarize again. If n is odd, you know they're going in opposite directions. Okay? You know the x is going to be one's going to be a negative infinity, one's going to be a positive infinity. Always. Okay? If the a is positive, then these two signs are the same for odds. Okay? If a is negative, then these two signs are opposite. You know this is going to be a negative infinity, that's going to be a positive infinity. All four of them are going to be infinities. If it's an odd n, so they're going opposite directions, then and a negative a, then that's going, those signs will be different, these signs will be the same. If it's an even n, they've got to be the same signs for your f. Okay, one x is going to be negative, one positive, one x negative, one positive, they're all infinities. And if the n is even and the leading coefficient is negative, these are going to be the f's are in the same direction, and they're both going to be positive. For a negative, they got to be the same direction, so your f's are going to be negative. Okay. What I do, I just pick the number 10. Plus 10 or minus 10, raise it to whatever power that n is. It's going to be a huge number, and then say, and if it's a negative, it's going to be a negative 1,000. A positive. Yeah. It's pretty easy to just use not that big a number, 10, but when you raise it to a high power, it gets big pretty fast. Sorry, I've got hiccups. So that's page 125, leading term test. They call it leading coefficient test. Here's example 2. Describe the right hand and the left hand behavior of the graph of each function. So how am I going to write this? Maybe something like this. As x approaches blank, f of x approaches blank. And as x approaches a different blank, f of x is approaching some blank. And we're going to say the same thing for all three of these. I was hoping they'd give them G and H, but they're all X's. So what will it be on the first? What can you fill in right now and know you're going to be at least partially right? For what? Okay. You want the first X to be positive infinity? What does the next X have to be? Negative infinity. And you can do it in any order you want to. I don't care. I don't want to put any requirement on it. Okay. Now, what's your f of x doing is x is going to positive infinity. It's going to negative infinity. They're all going to be infinities. Go on and put all infinities out there, okay? And that's going to a negative infinity. Why? Because instead of infinity, take 10. 10 cubed is 1,000, negative that is negative 1,000. That's going south pretty quickly, okay? And then, as x goes to negative infinity, well, let's not use infinity, let's use 10. As x goes to negative 10, negative 10 cubed is negative 1,000, but then when you negate it, it becomes positive 1,000. So that goes just to infinity. You got it. Done. Enough said. These should be pretty easy points, right? Filling in these blanks. Okay? Let's do this one. As x goes to blank, f of x goes to blank, and as x goes to blank, f of x goes to blank. Okay? You tell me what to fill in where. Which one? For X? Okay, negative infinity, I'll buy that. And what should I then go and fill in the other one? X going to positive infinity. Pick one, doesn't matter which, they're all going to be infinities, so pick one to be positive, one negative for your X's. Not for your F, for your X's. Okay? Now at this point, let's take a, rather than negative infinity, negative 10. Negative 10 to the fourth power is 10,000. Positive. So f of x is infinity. And when x goes to infinity, let's use 10 instead. 10 to the fourth power is 10,000. Okay, that's going to positive infinity as well. All four of those are going to be infinities. Okay, one x is going to be positive, one negative. It doesn't matter what order you do. And then evaluate your f of x based on that. Okay? And what that is determined by is, number one, the even or oddness of your exponent, and number two, the sign of the coefficient. That has a coefficient -1, this is a positive. Okay, how about this one? Same deal. As x goes to blank, f of x is going to blank, and as x goes to blank, f of x is going to some other or same blank. Okay? What do you fill in first? Second? Infinity for x. I take it you mean positive infinity? Okay. What goes in some other blank? For the other x. Okay. If one is positive, the other is negative. That one's always true. Okay? Now, again, here's how I like to do it. Rather than remembering the rules, just do this. Take it to be 10. That's not infinity. It's nowhere close to infinity. So let's take 10. 10 to the fifth is 100,000. Positive or negative? Positive. So that's just going to be a positive infinity. Okay? And as that goes to negative infinity, let's just use negative 10. What's negative 10 to the fifth? Negative 100,000. That's heading toward negative infinity. They're all going to infinity. You just fill in infinity in all four blanks, make one x positive and one negative, and then determine the signs of the others. I like using 10. However, if you like the rules, use the rules. Okay? You okay with it? Any questions? Do you see how to do it? Okay? This just tells you end behavior. When you're going to sketch the graph of one of these big, hairy, complicated-looking functions there, polynomial functions, with some big old exponents, you can start off by going, well, this one's going this way, this is this way, or that way. Yeah. You can draw your arrows where they're going to head in the long run. Okay? And then after that, you can go back and do your other stuff. Always start with the end behavior. Left-hand behavior, right-hand behavior. Okay. Let's see what they do. All right. For that first one, degree is 3, which is odd, means opposite directions. Okay. And the leading coefficient is negative. Okay. This is using just the rules. Then you know that they're going in opposite direction, and because the leading coefficient is negative, it's opposite what you would think. A negative x is going to be a positive y, a positive x is going to be a negative y. Okay? Because the degree is odd, they're going in opposite directions, the leading coefficient is negative, they're going in the opposite direction from what you would expect. Okay? There you have it. And they drew through the whole graph. We really weren't interested in what the rest of the graph looks like. What we're interested in is the end behavior. And that's what we got. Okay? The second one, what can you tell me about it? coefficient, leading coefficient is positive, and it's not just positive, it's always positive. Even, okay. So that means it's either even coefficient means they're going in the same direction. A positive leading coefficient means it's going positive. So both of those are going positive. That's all you really needed to know for this problem. They graphed the whole thing, but that's what you got. It's only up and up. Okay? Then this one, leading coefficient, or leading term, what does it tell you? Positive leading coefficient and odd exponent. Odd exponent means it's going in the opposite direction, but because the leading coefficient is positive, it's going in the same direction as the x. So if x is going negative, y is going negative. X going positive, y is going positive. Very good. All right? Now, these figures they did, we didn't have to. We were just looking at the end behavior. They drew the whole figures here. But they tell us something too. Okay? Let's go back and look. What's the degree of that polynomial? Say again? Cubed is 3. Okay? Now, how many changes of direction do you have? 2. Here we have a valley here and a hump there. 2 changes of direction. Okay? 1 less than the 3. Okay? What is the degree of this one? 4. How many changes of direction do we have? 3. 1 less than that. Okay? But don't get your rules in place yet. Tell us what's your degree here. 5. But how many changes of direction? 2. Can't ever be more than n plus 1, but can be less than n plus 1. Okay? So, that would have a maximum number of changes of direction of 4, but it then could be less than that as well. And this only has 2. Now let's go back and look at something else. What's the degree of that polynomial? 3. Okay. How many zeros does that one have? 3. It crosses the x-axis here, and there, and there. So it has 3 zeros. So, how about this one? What's its degree? How many zeros does it have? At most 4. Can't have any more than 4. But it doesn't have to have that degree. What's the degree of that one? How many zeros? 3. So it's 5 or less. Every one of them is up to the degree, but no more. May have fewer, okay? In fact, if you give me a number bigger than 4, okay? 6, I like 6, okay? Now, here's why. If it was 6, everything's going to be shifted up by 2. So this is a 4, 6. Then the W looks like this. How many zeros do you have? Now let's go back to your 5, and then you would just come down and touch here, go up here, and then touch here again. How many zeros would you have there? 2. So you see it's always n or less. Could even be 0. But here's a hint. What's your degree here? 3. What is that? Even or odd? Odd. Because the end behavior for odd is always in the opposite direction, this one's always going to have at least 1 0. You can't get from there to there without crossing the x-axis somewhere. This crossed it 3 times. If you had raised this way up here, still going to have to cross it because it's going to negative. Right? So for an even function, you may have no zeros. For an odd function, you're always going to have at least 1. You could have up to n, but you're always going to have at least 1. Same with even. You could have up to n, in this case 4, but you could have 2, you could have 1, you could have 0, you could have 3. I mean, there's any number less than n, including 0. But for an odd, you can't get a 0 ever. Always going to be either 5 or 4 or 3 or 2 or 1, but not a 0. Okay? Now that's beyond what this is doing, but since I had such nice graphs here for us, I thought we'd use those to our advantage. So, in example 2, which we just did, note that the leading coefficient test, I like to call it a leading term test, tells you only whether the graph eventually rises or falls to the right and to the left. That's all it tells us. The other characteristics of the graph, what's going on in the middle there, such as intercepts, minimum and maximum points, must be determined by other tests. I've already given you a hint on some other things that you can use, but it doesn't tell you what they are. It just tells you how many you might have. Okay? So, this is top of page 127, real zeros of polynomial functions. Okay. This is what I was just telling you. It can be shown that for a polynomial function f of degree n, the following statements are true. How many real zeros could you have? At most. N. Okay? You could have at most n zeros. You don't have to have that many. You could have at most n real zeros. So you're going to have n or fewer. The graph of f has at most how many terms? N minus 1. Okay, n minus 1 turning points. Turning points, also called a relative minimum or a relative maximum. Okay, points at which the graph changes from increasing to decreasing or decreasing to increasing. Okay, so these are the two things we just were noting on those things. I knew this was coming up, but I wanted you to see it on the graph first. Okay, finding those zeros of the polynomial function, one of the most important problems in algebra. Why would finding those zeros be sort of important? What if you had a business and you had costs and you had expenses? You're really interested in where your break-even point is. That for cost equals expenses. Then anything past that, you're going to have profit. Anything short of that, you're paying out. Okay? I grew up on a farm in Georgia. My father was a full-time farmer. And it was hard. It was fun, though. It was, hard work, but it was rewarding. You produced a crop, you sold the crop, you produced the cattle, whatever. And my father was a very good manager. We never had a lot of money, but we always ate really well because we had chickens, we had pigs, we had cows, and we had vegetable garden, so we ate great. Okay, nobody I knew ate better than I did. Okay, but we never had very much moulon. Okay, moose for the cows, yes, but not the lots. Okay, so he was able to support a family of 6 with the farm. Now my younger brother always wanted to farm. Okay, but he also was a really high liver too. So he had to have an outside job. He couldn't make it just on the farm income. So he worked his whole career, and he did well. He was vice president, wound up being vice president of a small electric power company. So he did well. He saved money well. He did all things, but he always invested in the farm. So when he retired, he could, farm full time. That was his dream. Well, he kept putting off his retirement, and finally retired last year. And for that last year, since he waited until after January 1st to retire, then he got to spread his unused leave and sick leave and everything else over the whole year. And it was like he had full income, but he wasn't working. He was there on the farm. And since he was there full time, he was working really hard full time. Actually lost weight, wasn't sitting around the desk most of the day. So he was feeling pretty good about himself until he saw he was still having to invest in the farm from his salary. He said, hey, next year, I'm not going to have this salary. I'm going to have his retirement, stuff, which is going to be significantly less than what he was making then. He's not may be old enough for Social Security at the reduced level now. But he said, I can't go on supporting the farm with my income. He had been doing that his whole working life because he wasn't. Well, times have just changed. All the equipment's more expensive, the taxes are more expensive, the weather is less predictable. I mean, everything was just sort of, and he said, I can't afford the farm anymore. His whole working life, he had farmed on the side, looked forward to retiring so he could do, but found out he had all that time been supplementing the farm with his income. And he said, no, now that I retired, I don't have enough income to supplement the farm. I'm selling the cows. And literally he is. He called over the weekend, I guess it was Sunday night. I was trying to get some work done here. So just telling me all his stuff here. So it's, he found out his zero was down there, not here. Okay. He wasn't going to make it with the farm anymore. So what we're doing is selling the cows, planting pine trees, and then if he lives long enough, he'll have income from the pine trees. But if he doesn't, his kids will have income from the pine trees. But we get a better tax deal with the pine trees as well. So anyway, finding those zeros of the polynomial functions is one of the most important things. He found out in the last year his zero was below zero. Okay, he was not going to make it. Is it time already? All right. Where we're going to start next time is real zeros of polynomial functions on page 127. Before you go, let me give you a few homework exercises, because I know you want to have some of those to do. Any of the odds, I would do all of 9 through 14. The odds are going to be in the back of the book. Okay? Then do any of the odds, and by the way, they're all at calcchat.com. Any of the odds 15 or 17, they're both at CalcChat, thank you. And 17's at CalcView.
I'm going to take the test.
I'm sorry?
I'm going to take the test. I don't take it.
Okay, just a minute. Let me finish this. I'll get with you. Okay, any of the odds 19 to 27, all of them are at CalcChat. 21's at CalcView. If you've got a graphing calculator, try to do 29 or 31. You might be able to answer some of the questions without that. And we'll stop there and we'll do real zeros next time. All right. Let me go on and end.